Hi everybody, welcome to the last video in differential equations, section 9.5 to 9.7. In these sections, we study the matrix form of the differential equation and we try to solve differential equation using a matrix. If you have taken linear algebra, this will be a little bit easier. If not, it will be something new. Alright, so first, in order to write the solution for differential equation, we need to have eigenvalues and eigenvectors. If we have A is an n by n matrix, so that is the square matrix. The eigenvalues of A are those real or complex number R such that A minus R times identity matrix times the vector U is equal to 0 vector has at least one non-trivial real solution. The corresponding non-trivial solution U are called the eigenvectors associated to that eigenvalues. So eigenvectors and eigenvalues are a pair. Eigenvalues is a number, eigenvector is a vector, they associate to each other. Alright, so we need to pay attention to two things. First, to get the eigenvalues, we will solve this one, which is called the characteristic equation. So determinant has to be equal to 0. That is called the characteristic equation. If we don't have the 0, then we have the characteristic polynomial. And to solve for the eigenvectors, we're going to solve for this one, that equation. So this equation is to solve for eigenvectors. This equation to solve for eigenvalues. We solve for eigenvalues first, and then we solve for eigenvectors. Right. So this equation to solve for eigenvectors, and this one to solve for eigenvalues. Right. Let's just look at the first example, and then we'll explain more what the actual eigenvalues and eigenvectors are. Right. Now just find the eigenvalues and the eigenvectors of the matrix, square matrix. So first, we set up the characteristic equation, meaning that we're going to take the matrix A, subtract R times the identity matrix, 1 on the diagonal, 0 everywhere else. We take determinant and equate that equal to 0. So we know how to take determinant, right? So basically, we just have the matrix A right? Basically what we do is we just subtract R on the diagonal, find determinant equal to 0, and then solve for R. So this one's clear, right? Just subtract R on the diagonal, find determinant equal to 0. So I find the determinant, multiply and subtract equal to 0, have plus 1 or minus 1. So that is the eigenvalues. Next, to find eigenvectors. Eigenvectors will be associated to eigenvalues. So there are two eigenvalues. So first we have eigenvalues of 1. So we do the same thing, A minus 1 times I. So pretty much what we do here, instead of do all of that, you can just write the matrix A, 2 minus 3, 1 minus 2, right? That is the matrix A. What we do is we just subtract the eigenvalues on the diagonal, multiply by the matrix equal to 0, 0. That's exactly what we have here. And then simplify, we have 1 minus 3, 1 minus 3 equal to 0. Now, if this is a 2 by 2, this is easy. We don't have to do the reducible echelon form. Those two equations will be multiple of each other. So we can just take any of them. Right? If the eigenvalues is correctly found, when we have a 2 by 2, we have two rows. One of them is the multiple of others of each other. One row is the multiple of the other, and sometimes they are identical like this. So all we do is we can do long-winded like this, or we can just say, if we take this equation and we rewrite this as equation, what do we have? u1 minus 3u2 equal to 0, right? Now, when we do the reducible echelon form, remember we did this on the previous section. If we have the 1, that is basic. This one is not 1, so we're going to let u2 to be arbitrary. So in that case, you can rewrite as u1 equal to 3u2, right? So you can say u1, u2 equal to u1, 3u2, and then u2. Factor out u2, we have 3, 1, u2. And this is the eigenvector associated to 1, to eigenvalues 1. Right? So now when we write the matrix A minus Ri times U equal to a 0 vector, I multiply it out. I have A, U, and multiply this. I just have R times U. It's a vector equal to 0. Or we have A times U equal to R times U. So the significance of eigenvalues and eigenvector is this. Is that if I have the whole matrix times a vector, for some certain type, for certain numbers and certain vectors, instead of I use the whole number, the whole matrix multiplied to the vector, it is just equal to a number times the vector. So that is the significance. We can write the vector times the matrix times the vector equal to a number times the vector. Of course, this simplifies a lot. So we're going to need to have R, U. So that is the significance of eigenvalues and eigenvector. It turns a matrix times a vector into a number times a vector. But that vectors is eigenvectors, and R is eigenvalues associated to that eigenvector. Right. Second example, second part, we have eigenvalues R equal to -1. So once again, we will have the original matrix. Now we have the eigenvalues of -1. I subtract that, meaning minus -1, just plus 1 on the diagonal. Multiply u1, u2 equal to 0, 0. Right, that gives us 3, -3, 1, -1. Right. Of course, if it is 2 by 2, we don't really need to do reducible echelon form. We don't really need to do that. It's going to be, but if we do, it's going to be in this form, and then we multiply it out from the top equation. Give us u1 minus u2, u1 minus u2 equal to 0. So here we can say u1 equal to u2. So if we write the vector u1, u2, u1 is equal to u2 and u2 is u2. Factor out u2. Factor out u2, sorry. We have 1 and 1 times u2. So 1, 1 is the eigenvector associated to -1. By the way, eigenvector is not just a unique vector, it could be anything, right? Of course, we have u1 equal to u2, so it could be 2 and 2, it could be 3 and 3, or as long as u1 equal to u2, we have that eigen vector. And in linear algebra, so we call this as an eigenspace. So it will be the whole space where u1 equal to u2, where two components are equal to. So if it is on the plane, we have x equal to y pretty much. So that is kind of the diagonal line. All right, so let's look at the first example and see what can we do. So first, eigenvalues, then eigenvectors. For eigenvalues, we're going to find the determinant, which is a straight line a minus r times I. Determinant of that equal to 0. But in terms of calculation, we don't even need to write like that. All we need to do is just we have the matrix 8, 1, 11, and minus 2. All I do is I will subtract r on the diagonal. Determinant is supposed to be equal to 0, right? Straightforward. Just subtract the r to the diagonal, and I will do the math. The determinant. So cross multiply a minus r, negative 2 minus r equal to 0. I'm sorry. Cross multiply and then subtract the other direction equal to 0. Now we multiply them out. Negative 16, negative 8r, plus 2r, plus r squared, minus 11 equal to 0. Combine like terms, we have r squared minus 6r minus 16 and 11, that's 27, right? Right? And then we factor that more like the r minus 9 and r plus 3, right? So if r1 equal to 9 and r2 equal to negative 3. So those are the two eigenvalues. Right, so simple enough, right? For that, to solve for this equation, it's called characteristic equation, and we have the eigenvalues. Right, simple enough. Next, eigenvectors. We have two eigenvalues, r1 equal to 9, r2 equal to negative 3. We have to solve for each one. First, for r1 equal to 9. Right. For eigenvectors, what we solve for is solve for u in this equation a minus r times I times vector u equal to a 0 vector. So this is the matrix equation. Right, so this a r minus I is simple. So this is determinant, but this is matrix a 1, 11, minus 2. What I do is I subtract the eigenvalues on the diagonal. And then u 2 by 2, so we have u1, u2 equal to 0, 0, right? Now simplify this, what do we have? 1, I'm sorry, negative 1, 1, 11, negative 11, and U1, U2. If the eigenvalues are correct, we're supposed to have one row is the multiple of the other row. If we have a 2 by 2 matrix, that's what we have. Usually, if it's 2 by 2 matrix, we're just going to take the first row and go directly to our calculation. But later on, we have 3 by 3, then we have to use reducible echelon form. But for 2 by 2, don't need to do that. Just go straight from here. By the way, I'm just going to do the first one. Right? Take the first one. By the way, for this one, the corresponding matrix is negative 1, 1, 11, negative 11, and then the other side 0, 0. Right? So that is the romantic matrix. If we use reduced row echelon form for this matrix, we did this on the previous chapter, right? Previous section. So second matrix, reduced row echelon form, do that to the matrix. Negative 1, 1, 0, 11, 11, negative 11, right? Of course, when we do that reduced row echelon form, we will have 1, negative 1, 0, 0, right? But if we write that instead of in the matrix form, we will have what? Negative 1, I'm sorry, 1, negative 1, 0, 0, U1, U2 equal to 0, 0. Yeah. So we can write in the romantic matrix or in the matrix form. Those will be the same. Right? Now, what we have earlier in previous section, whenever we have 1, those are the basic. If the first entry is 1 on the row, then that column is a basic. So this is the basic column. This is non-basic. So we're going to choose U2 to be arbitrary because there's no leading 1 in this row, in this column, right? So we choose U2 to be arbitrary. Right? And then from this equation, we can write as U1, 1U1 minus U2 equal to 0. So what do we have? U1 equal to U2. So U2 is arbitrary and U1 is equal to U2. So now if we write the matrix out, the matrix form as U1, U2, U1 is equal to U2 and U2 is U2. So factor out the U2, we have 1 and 1, U2. So we can say 1 and 1 is the eigenvectors. And I will write eigenvector is going to be 1 and 1. Alright, by the way, if you take in linear algebra, you probably do not do any of this step. For the arbitrary, you can choose from this equation. We choose something that make it nice and even. You can choose U2 to be 5, then U1 is 5, and you choose the eigenvector to be 5 and 5. That is perfectly fine. Here I just write that in arbitrary. But in linear algebra, we can just choose U2 to be 1. Then U1 is equal to 1 as well, and that is the eigenvector. Right? So we can choose U2 to be anything, and then U1 equal to that. That's the eigenvector. Anything will work. Right, so that is the eigenvectors that corresponding to eigenvalues of 9. Now, to find the other eigenvector corresponding to -3, do the same thing. The vector of originally 8, 1, 11, -2. We subtract the eigenvalues on the diagonal. Subtract -3, that's +3. U1, U2 equal to 0, 0. So we have 11 and 1, 11 and 1. If it is in linear algebra, you can say those two equations are the same. 11 U1 is plus U2 is equal to 0, right? Meaning that we just take the first part here, we say 11 U1 plus U2 equal to 0. And then let's say choose U2 to be 1. Then U1 equal to -1 over 11. And we have the vector -1 over 11 and 1 as eigenvectors. That certainly works. We don't have to go any further. That gives us the eigenvector. Now, however, sometimes we have 3 by 3 and higher matrix. So usually I will rewrite this and use the reducible echelon form just to simplify it, and then we'll see it will be better, right? Of course, you can store the matrix too. Store to the matrix A is that 11. I'm sorry. 2 rows, 3 columns. All right. 11, 1, 0, 11, 11, 1, and 0. It is silly, but when you go to 3 by 3, we do the same thing. So reducible echelon form apply to matrix A. Yeah, we can write like that. So if we do the reducible echelon form, we have 1 over 11, 0, 0. Yeah. Reducible echelon form, we should have 0, 0 at the bottom. Right. So I don't have to write the associated augmented matrix. I just write the matrix equation directly. Reducible echelon form equal to that. Now, once again, we have the 1 here, right? So what I do is choose U2 to be arbitrary. We can choose just 1 if we want to. U1 is arbitrary. And then from the first equation, we have U1 plus 1 over 11 U2. So we can say U1 is equal to -1 over 11 U2. So we can say the vector eigenvector of U1 U2 equal to -1 over 11 U2, and U2 is just U2. Now factor out U2, we have -1 over 11 and then 1 U2. Of course, we can find the eigenvectors of -1, 11, 1 over 11 and 1. Now, for simplicity, sometimes we just say if we let U2 equal to 11, then multiply in, we're going to have much better vector, right? -1 and then 11. sometimes we choose a number so that there's no fraction. So in this case, the eigenvector u2, notice that u2 is a number. This u2 is an eigenvector of -1 and 11. Right, that's simple enough. That gives us eigenvalues, eigenvector. So eigenvalues solve this equation. Eigenvectors solve for this equation, and then just factor out u2 or whatever the variable is, the independent variable, the arbitrary variable we should have, the eigenvector. Right, how about we have a 3 by 3? Will be the next example. By the way, just a quick check, when we have a matrix, 2 by 2 matrix, what we have here, what we define to be the matrix A, trace of A is going to be the sum of these two entries, the sum of the diagonal entries. In this case, trace of A is equal to 8 minus 2. Just add them, add the entries in the element, in the diagonal. That gives us 6. And the determinant of A, that is A times -2 minus 1 times 11. So minus 16 minus 11 minus 27. It can be shown that for 2 by 2, the characteristic equation is that characteristic equation. If we have the trace and we have the determinant, it's going to be r squared minus the trace of A, r plus the determinant of A equal to 0. Sorry. So r squared minus trace of A times r plus determinant of A. If we look at the first equation, the trace 2 minus 2 plus -2 is equal to 0. So in this example, we calculate trace of A is equal to 0 because 2 minus 2 is 0. I just write out. And determinant of A is 2 times -2 is -4 minus -3 minus 4 plus 3 is -1. So the equation is what? R squared minus trace of A, r plus determinant of A equal to 0. So r squared trace of A is 0, so we have 0r. Determinant of A is -1. So if it is a 2 by 2, it's going to be r squared minus trace of A times r plus determinant of A. Or we can just multiply it out. Either way. Right, now we have a 3 by 3. Okay, same principle, just a little bit more work. Right, so let's start with eigenvalues. Eigenvalues is to solve the equation determinant of A minus Ri equal to a 0 number. That means I find the determinant of this matrix 1, 2, -1, 1, 0, 1, 4, -4, and 5. That matrix, yes, but we have to subtract r on the diagonal. That essentially A minus Ri means. And determinant of that has to be equal to 0. So this is a characteristic equation. Just the matrix, subtract r on the diagonals, find determinant equal to 0. Right, 3 by 3 determinant. We did this before. 1 minus r. And then for that entry, we cover the row and a column containing that entry. So we're going to have -r and 1, -4, 5 minus r. Right, next, subtract. Now I'll evaluate based on the first row. Subtract 2. Now cover the row and the column that containing 2. We left with what? 1, 1, 4, 5 minus r. And then the next one is minus 1 times cover the row and the column containing that entry. We have 1, negative r, 4, negative 4 equal to 0. Multiply this out. Negative r times that. Negative r times, just write this out. Negative r, 5 minus r, minus negative, so that's a plus 4. Minus 2. 1, so it will be 5 minus r. 1, subtract that direction, 4 times 1 is 4. And then minus negative 4. That's plus 4r equal to 0. Multiply it out. 1 minus r minus 5r plus r squared plus 4. And then this 5 minus 4 is 1 times 2 minus 2, and minus 2 times minus r plus 2r. And then plus 4 minus 4r. Right, multiply this one more time. Multiply by 1, so I just copy it. Now multiply by r, negative r, so that plus 5r squared minus r cubed minus 4r and then the rest, negative 2 plus 2r plus 4 minus 4r equal to 0. Hopefully I did not make any mistake yet. Right, r cubed, there's only one r cubed. R square, how many r square we have? 1, 2. Those are r square. 5 and 1, that's 6 r square. Look right so far. And then the r, negative 5, negative 4 plus 2 and negative 4. So negative 9, negative 13 plus 2, negative 13 plus 2, negative 11r. 1, 4 plus 4 minus 2, 6. It's going to be 6. Right, hopefully we have something nice and even here. Right, negative x cubed. I'm just going to graph it and see if there is any intersection with the x-axis, and that would be the 0. Right, look nice. Let's zoom in Okay, 1, 2. Just go to table then. Right, 1, 2, and 3. It's nice. So that could be the equation we have r equal to 1, r equal to 2, and r equal to 3. Yeah, of course we just do the factoring, we have that, but just look at the graph, the intersection, the x-intercept 1, 2, and 3. So those are the eigenvalues. Alright, we have it. Now the eigenvectors. There were 3 eigenvalues. There should be 3 eigenvectors. First, for R1 equal to 1. And for in the eigenvectors, we show for equation A minus Ri times vector U equal to a 0 vector. So what I do is the matrix A, the matrix A, 1, 2, negative 1, 1, 0, 1, 4, negative 4, 5. I just subtract the eigenvalues on the diagonal. This time eigenvalues is 1. Multiply by U1, U2, U3 equal to 0, 0, 0. Right. Simplify this. Write it here. 1 minus 1, 0, 2 minus 1, 1, negative 1, 1, 4, negative 4, and 4. As you see, those two rows look like the multiple of each other. But we're not going to just take that, because when we have 3 rows, one may not be the multiple of the others. But we know that they are linearly dependent. So what I usually do, just to be safe, just go ahead and do the reduce row echelon form. If it's a 2 by 2, just take 1 row and just do the math. But if it is 3 rows, cannot do that. So if I look at second matrix, go to math, reduce row echelon form, and the matrix. All right, I will enter the matrix directly in the home screen. We have 3 rows and 4 columns. Zero, 2, negative 1, 0, 1, negative 1, 1. I didn't enter 1. Right. 4, negative 4, and 4. Right. We can just keep this 0.5. That's perfectly fine there. So we have 1. If we do correctly, we should have a row of 0 at the bottom. I write this in the matrix form though, not in the augmented matrix. Right. Now look, this one we have 1. That is the pivot one or the leading one. So this column is basic, this column is basic, this column is not basic, but so we're going to let U3 because that corresponds to U3, so U3 is arbitrary. And then from the top equation we can say from this two row can we write U1 plus 0.5 U3 equal to 0, right? The first row. A second row we have U2 minus 0.5 U3 is 0. Now so for U1 you have 0.5 U3 and U2 0.5. This is negative 0.5 U3 and the other one is positive, right? So we write the vector as U1 equal to U1, U2, U3 U1 negative 0.5 U3 0.5 U3 and then 1 U3. Factor out the U3 we have negative 0.5 0.5 and 1 U3. And now if we choose U3 to be 2, so we don't have to deal with the half. So U3, let's choose to be 2. And to multiply this inside 2 times that give us negative 1. 2 times that give us 1, and 2 times 1 is 2. So negative 1, 1 and 2. Right. So that is the eigenvector U1. Look like we might not have enough space. So let's just try to squeeze in as much as we have here for R2. Equal to 2. Right, so the matrix 1, 2, negative 1, 1, 0, 1, 4, negative 4, 5. And then minus 2 on the diagonal times U1, U2, U3 have to be equal to 0, 0, 0. Right. I try to write very small here. Right. So we have minus 1, 2, minus 1, 1, minus 2, and 1. 4, minus 4, 5 minus 2, 3. Right. U1, U2, U3 have to be equal to 0, 0, 0. Yeah, just subtract the eigenvalues on the usual echelon form. Right, -1, 2, -1, 0, 1, -2, 1, 4, -4, and 3. Right, so we have that 1, 0, 0.5, 0, 1, -0.25, that's 1/4, and 0, 0, 0. If we do correctly, we should have a row of 0 at the end. Right. Now with this, of course, then we can use once again 1 in first column and second column. So we choose U1, U2, U1 in terms of U3. U3 will be arbitrary. And let's just write this equation here. What do we have? U1 plus 0.5 U3 equal to 0. And this U2 minus 0.25 U3 equal to 0. So when we solve for that, we will have U3 is arbitrary. U1 equal to negative 0.5 U3, and U2, move that to the other side, 0.25 U3. And so we can write the Eigenvector I should write this smaller from the beginning. Anyway, U1 negative 0.5, U2 0.25, U3 is 1. So factor out the U3. And if I choose U3 to be 4 times this, it's going to be 1. So I don't want to deal with any fraction. So U2 is going to be equal to negative 0.5. 4 times 0.5 is negative 2. Negative 2. 4 times 0.25. 1. 4 times 1, 4. So this is the eigenvalues, eigenvector corresponding to the second eigenvalues. Next, eigenvalues is 3. Once again, we have the matrix. Just subtract 3 at the diagonal. 1, 2, negative 1, 1, 0, 1, 4, negative 4, 5. I subtract 3 on the diagonal. Times U1, U2, U3 equal to 0, 0, 0. Right. So that gives us the matrix negative 2, 2, negative 1, 1, negative 3, 1, 4, negative 4, and 2. Look like this is the multiple of that row. Right. I'll just do reduce row echelon form. If it works out perfectly, the last row should be 0. -2, 2, and -1, 1, -3, and 1, 4, -4, and 2. Right, so we have that. 1, 0, 0.25, or 1 over 4, 0, 1, -0.25, 0, 0, 0, u1, u2, u3 equal to 0, 0, 0. Once again, 1 and 1 here, so the last column is non-basic, so we say u3 is arbitrary. And then from this equation we will have what? u1 plus 0.25, u3 equal to 0. So u1 is equal to -0.25, u3, and u2 minus 0.25, u3 is 0. So u2 is 0.25, u3. Now put them together. Eigenvector will be the first one 0.25, and then 0.25, and then 1 times u3. And then if we choose u3 to be 4, so in that case we'll get rid of the fraction. u3 will be equal to -4, 4 times that is -1, 1, and 1 times 4. So this is the eigenvector corresponding to that eigenvalues. Right. Now, next. Oh, sorry. We see on that page. Now, in terms of the solution, we have after we have eigenvalues and eigenvectors, what do we do? Right. After we have eigenvalues and eigenvectors, this is what we're going to do. If all of them, the eigenvectors are linearly independent, then we just say the solution will be the linear combination of this solution. We say e to r1 t times the eigenvectors and that. So case 2, when we have the complex, in that case the complex eigenvalues will be alpha plus beta I, and then in that case we can find 2 corresponding linearly independent eigens vectors alpha and beta. Put that in this form. And when we have the repeated eigenvalues, right? So when we have more complicated, we'll see. We'll go back to those and study more details. By the way, on the test or the final, I'm not on the test. On the final, I won't ask you this because these 2 cases a little bit of work, and 3 by 3, as you see, take a lot of work as well. There's a lot of things to worry about in the 2 hours exam, so I cannot put too much on it. So expect to see case number 1 on the final, only case number 1. Right, now if we have the matrix, the matrix equation in that form, then we did this on the previous example. We have eigenvalues and eigenvectors. So in that case we say x1 is e to the r1t eigenvector 1, x2 e to the r2t eigenvectors, and then we do the linear combination and we have this. So this is the solution. Alright, next we have this initial value problem, so a little bit more work than it is, but we did this previously. That is in the example D. So see example D. We have eigenvalues 1, 2, and 3. That's from the previous example. And the eigenvectors, we have first vector -1, 1 and 2, u2, -2, 1 and 4, and u3, -1, 1 and 4. Right. So we will have the solution x1. All of them, this is a vector, so we're going to have e to the r1 and then the vector. So we just have e to the t multiplied to all of that, so we will have what? E to the t times -1, e to the t times 1, and then 2 e to the t, right? x2 e to the eigenvalues times t, and then -2, 1 and 4, -2 e to the 2t, e to the 2t, 4 e to the 2t, x3 e to the 3t, -1, 1 and 4. So -e to the 3t, e to the 3t, and 4 e to the 3t. Right, and the solution is the linear combination. So C1 x1 plus C2 x2 plus C3 x3. C1 -e to the t, e to the t, 2e to the t, plus C2 -2e to the 2t, e to the 2t, 4e to the 2t, plus C3 e to the -3t, e to the 3t, 4e to the 3t. Multiply the c to all of that, and then all multiply out. Negative c1 e to the t, negative 2 c2 e to the 2t, and plus c3 e to the 3t. That should be a negative e to the 3t. Right. And then c1 e to the t, c2 e to the 2t, c3 e to the 3t. 2 c1 e to the t, 4 c2 e to the 2t, and then 4 c3 e to the 3t. Right, so that is the general solution. Next, when t equal to 0, this matrix equal to negative 1, 0, and 0. So at t equal to 0, we have negative 1, 0, 0 equal to. Now, when t equal to 0, we have e to the 0 power. E to 0 power is 1. So all of the e is 1. So we just have negative c1 minus c2 plus c3 c1 plus c2 plus c3 2c1 plus 4c2 plus 4c3. By the way, this is a system of equation. We can write this as a matrix, and then we do the reducible echelon form. So we can write negative 1, negative 2, and 1, 1, 1, and 1, 2, 4, and 4. And then the variable c1, c2, c3 are all equal to negative 1, 0, and 0. Notice that what we have is negative 1, 1, and 2, negative 1, 1, and 2, negative 2, 1, and 4, negative 1, 1, and 4. So same as the eigenvectors here, because t equal to 0, e to t is equal to e to the 0 is equal to 1. Reducible echelon form. And then apply to the matrix here. Negative 1, negative 2, 1, and negative 1, 1, 1, 1, 0, 2, 4, 4, 0. And we have that. Right. So at the end, we know that C2 is equal to 1/3 and C3 is negative 1/3. Right. I actually paused the video and check one thing, and I think this will be a minus. But I didn't see it clear enough. So please change this to a minus. That should be a minus. And that should be the eigenvectors. Okay. sorry, that should be a minus 1. Right, much better. So I have a 1 and negative 1. So this is C2 is 1, C3 is negative 1. So the solution, C2 is 1, C3 is negative 1, C1 is 0. So this is the solution, C1 is 1. And so we have X equal to C1 is 1, C2 is 1, and C3 right. So when we have the solution is easy. C to the eigenvalues times T eigenvectors and linear combination of that. If we have initial value problem equal to that, and then we solve for the coefficient. In this case, that's what we have for the coefficient. Right. Next, we have more interesting problem. In this case, we have the repeated eigenvalues, but eigenvectors are linearly independent. Because when we solve for the eigenvalues, we might have the repeated roots. Right, so eigenvalues the solution is, the equation is determinant of A minus Ri equal to 0. So we have the determinant of the original matrix but subtract R at the diagonal equal to 0. Right, determinant 1 minus R cover the row and the column. And then this entry is going to be opposite to that. And then cover the row and the column. And then next one is 2. Cover the row and the column, negative 2, 1 minus R, 2 minus 2. Right, 1 minus R. Multiplying here, we have 1 minus R times 1 minus R. Subtract, negative 2 times negative 2 is 4. Plus 2 times minus 2 times 1 minus R minus negative 4 plus 2. Negative 2 times negative 2 is 4 minus 2 times 1 minus R. Right, multiply it out. Okay, what do we see here? Just multiply it out. Because when we simplify, over time we have the factor of 1 minus R, but yeah, that's not important. Just multiply this out. 1 minus 2R plus R squared minus 4 plus 2 minus 2 plus 2r plus 4 plus 2 4 minus 2 plus 2r. Right, multiply it out. 1 minus r times this minus 1 minus 4 and minus 4 and 1 is minus 3. Let's just simplify it one more step. 1 minus r squared minus 2r minus 3 2r minus 2 plus 4 2r 4 minus 2. Those two are the same, right? Doesn't matter. Multiply it out. 1 times everything. And then minus r times all of that. Then 4r plus 4, 4r plus 4. Combine like terms. There's only one r cubed. R squared 1, 2, 3 r squared. How many r do we have? 1, 2, 3, and 4. So 3 and 4 and 4, that is 11 minus 2. 11 minus 2. And finally 4 and 4 is 8 minus 3 is 5. Equal to 0. Right. Now this, if we are trying to put this in the calculator, minus x cubed plus 3x squared plus 9x plus 5. Look at the graph. Right. We have the solution is 5, and at negative 1 it is a double root. You can see at negative 1 is equal to 0, at 5 equal to 0, but the graph touches the x-axis, so there's multiplicity of 2. So if we factor, we can factor this as that, but it's not important. So we have 1 and 2 is equal to negative 1, and R2 is equal to 5. Right, so those are the eigenvalues. Apparently I expect we need more space than that. Right. Now to solve for the eigenvectors. Now you see there's a problem, right? Previously we have a 3 by 3 matrix. There will be 3 eigenvalues, 3 eigenvectors. That is the normal case. In this case we have only 2 eigenvalues. So let's just take a look. For eigenvalues of negative 1, which is multiplicity of 2 now. Subtract that in the orthogonal, we have this. Reducible echelon form, we have this. Now, what did we have earlier? If we have 1, the leading 1, that is basic, so 1 is basic. Non-basic, non-basic. Because of that, we choose U2 and U3 to be arbitrary. Right? So U2 and U3 that arbitrary. And the top equation give us what? u1 minus u2 minus u3 plus u3 equal to 0, which we show for u1 is that finally you can say u1 is equal to u2 minus u3, u2 is u2, u2 is u3, and split this out and factor out 1, 1, 0 times u2 and negative 1 and 1 times u2 times u3. I mean, this will be 3. And that's easy. This is one of the eigenvector and the other one eigenvectors. So that's why I do it this way, refer the reducible echelon form. If for some reason we have two eigenvectors coming out of it, then we say we could potentially have more than one eigenvectors for the repeated eigenvalues. Right. And then next, for eigenvalues 5, do the same thing, subtract 1, 5 on the diagonals, and we have this reducible echelon form. This one have a 1 here and a 1 here, so u3 will be arbitrary. And the top equation, we have that u1 minus u3 0. The bottom equation u2, the middle equation u2 plus u3 equal to 0, and we solve for it. Put that in this form, factor out u3, and we have this, and that is the eigenvector. And finally, the solution is e to the negative 1, which is the eigenvalues, times t, and times first vector, second vector, and the third vector, and then put them together. That is the solution. So even though the eigenvalues is repeated, but we find two linearly independent eigenvectors, so the solution is still the same. The problem is, if we cannot find the linear independent eigenvectors, then that could be a problem. Right? We do have an example like that too. Right. Of course, the section still continue, but I just want to stop the video because this looks like a very long video. So this is the first part of section 9.5 to 9.7. See you on the other side.